Okay, this is lesson 4 of module 7, simplifying square roots. So we know that we can simplify square roots of perfect squares, but in this lesson we're going to learn a method of writing a square root in a form that is simplified but not approximate. So we won't be estimating them like we were in lesson 2. But we will be rewriting them. So anyway, we're going to look at that together. So in this opening exercise, we're just asked some simple questions. What does the square root of 16 equal? It's 4, right? What is 4 times 4? Well, it's 16, which helps us to simplify square root of 16, right? And then does the square root of 16 equal the square root of 4 times 4? Yeah, it does. Okay, it's the same. Those are the same. Square root of 36 is equal to 6. 6 times 6 is equal to 36. So would the square root of 36 equal the square root of 6 times 6? Yes. Okay. All right, so we're just looking for some patterns in these equalities. What is the square root of 121 equal? It's 11. 11 times 11 is 121. Does the square root of 121 equal 11 times 11? And we'd say yes, it does. Okay, and so on. Square root of 81 is 9. 9 times 9 is 81. And does the square root of 81 equal the square root of 9 times 9? Okay, it does. So what would be another way to write the square root of 20? Well, if we can write square root of 81 as the square root of 9 times 9, I could write the square root of 20 as the square root of 4 times 5. Okay? How could I write the square root of 28? I could write the square root of 28 is equal to the square root of 4 times 7. And there's other ways I could do that too. Another way to think about this is, let's just back this one up. Since 28, I know that 28 is equal to 4 times 7. I know that I can take the square root of both sides of that equation, right? Is equal to the square root of 4 times 7. All I'm doing is changing what's under the radical, just rewriting it. Okay, so this is leading into a method that we're going to use to simplify square roots without having to approximate them. All right, so if I have the square root of a number that can be written as 2 factors, a and b. So in the case of 20, that would have been 4 and 5, right? If I have a square root that is the square root of a times b, I can rewrite that as the square root of a times the square root of b. So what that's going to allow me to do is to see if there's any perfect square factors. So if one of these, if a or b is a perfect square, when I rewrite it like this, part of this expression can be simplified exactly, because perfect square roots of perfect squares, I can just rewrite them as the number itself, right? So that's what we're going to be doing. We're going to be looking at numbers that are not perfect squares and seeing if they have any factors. But before we use this, and I don't want you to just accept that this is true, we're going to prove it, okay? Because that's what we do. We prove things. Okay, so we're going to prove that these two things are equal. We're just going to prove this for square roots. So I'm going to say let C equal the square root of a times b. Okay, that's half of our equation. And I'm going to let D equal the square root of a times the square root of b. Okay, so I've got those two things. So I've defined C as a square root of A times B, and D as the other side of that equation. I'm going to square C. If I square C, C squared, I can square both sides of this equation, right? C squared is equal to the square root of A times B squared. So C squared is equal to the square root of A times B times the square root of A times B. I just wrote that twice, all right? Okay, so you're following me? C squared, if C is this expression, then C squared is that expression squared, and that thing squared is just that thing used as a factor twice, right? So I just wrote it like that. But what is this expression here? I've got the square root of this number times the square root of the same thing. And what is that? Well, if I take the square root and multiply it by itself, this is just A times B, isn't it? Okay, if C squared is the square root of if C is the square root of A times B, then C squared is A times B itself. Okay? All right, so let's hang on to that for just a minute. Let's square D. Okay, what is D squared? D squared is equal to all of this stuff over here squared. So I'm going to say square root of A times square root of B times that again, square root of A times square root of B. Okay, now I'm going to rearrange these things. So D squared is equal to, I'm going to use this, I'm going to use the associative property or the commutative property of multiplication. This is equal to, I'm going to put square root of A times square root of A times square root of B times square root of B. Okay, so D squared is equal to this. What's square root of A times the square root of A? Well, it's just A, isn't it? Because that's the definition of square root. And what's the square root of B times the square root of B? Well, it's just B. Okay, so now I have D squared is equal to A times B. Okay, so what I want to prove, I want to show that C equals D. Okay, because if I can show that C equals D, then I know that this statement up top is true. Let me outline that in, let's go with green. This is what I'm trying to prove. I'm trying to prove this whole thing right here. So if I can show that C is equal to D, then I'll know that square root of A times B is equal to the square root of A times the square root of B. Okay? But I know now that C squared is equal to D squared, right? So, I need a tiny bit more room. Let me just get rid of this. Okay. Okay. So I've done this. So I've shown that, now I know that C squared equals D squared. All right. Don't you love these proofs, guys? So C squared is equal to D squared, right? I know that from these two things. Since they're equal to the same thing, they're equal to each other. So C squared equals D squared, but watch what I can do. I can take the square root of C squared, and that equals the square root of D squared. Square root of C squared is C, square root of D squared is D, so C equals D. Okay, so we have proven that C equals D down here, so that means that this is true up here. All right, so hang on to that, and we're going to do some examples, and I'm going to show you how this this can be useful in writing expressions in a more simplified way. All right, so let's look. Simplify the square root as much as possible. Okay, so square root of 50. I know that the square root of 50 is really close to the number 7, right? Because 7 times 7 is 49. So square root of 50 is just a little bit bigger than 7. But that's not an exact answer. That's great if I want an estimate. But if I want to keep it in its exact form, that's not going to be good enough for me. So I want to simplify this square root by seeing if it has any square factors. So I'm going to rewrite square root of 50 as the square root of 25 times 2. So that's kind of my A times B, right? And now what I can do is write this as the square root of 25 times the square root of 2. Okay, and now I can rewrite the square root of 25 as 5, and the square root of 2 I'm going to leave alone. And then the way we write this is we leave out the multiplication sign and we just write 5 square root 2, and that means it's being multiplied. Okay, so this is considered a simplified form of this expression. They're going to have exactly the same value numerically, but they look a little different, and this is more simplified because what's under the radical sign is a smaller number. Okay, so I've got a 2 under the radical sign instead of a 50 under the radical sign. Okay, so this is simplified form of that. Okay, so what we used was we used this, that the square root of A times B is equal to the square root of A times the square root of B. Okay, let's do another example. So 28 has a perfect square factor because it can be written as 4 times 7, right? So square root of 28 is the same thing as the square root of 4 times 7, which is equal to the square root of 4 times the square root of 7. And then I can simplify square root of 4 to 2, and square root of 7 can't be simplified any further. So that's 2 times the square root of 7. All right, so there's the simplified form. Okay, I want to just convince you again that this identity works. So we'll call it that. The square root of A times B is equal to the square root of A times the square root of B. Okay, so consider the square root of 36. Now that's a perfect square, and I know that it equals 6, right? Square root of 36 is 6. But what if I rewrote it? Square root of 36 could also be written as the square root of 4 times 9. All right, and I can take then and I can simplify this according to this rule up here. And I can write it as the square root of 4 times the square root of 9. Those are both perfect square factors, which is kind of cool. So the square root of 4 is 2. The square root of 9 is 3. And so that equals 6. Okay, so I broke it apart a different way. You know, I thought of it, the square root of 36 is equal to the square root of 6 squared, which is equal to 6. Or I can think of it as 4 times 9 and do it another way. Okay, so that's just kind of an additional proof here of, or an example of the fact that that this rule up here at the top of the screen right up here works, that it is true. All right, so let's do some more examples. So exercises 1 through 4. Simplify these square roots as much as possible. So you can go ahead and work on those if you're feeling confident. go ahead and work on those and then come back and check your answers, or if you'd like to check your answers one by one, then you can do that too. So go ahead and pause the video now and see if you can simplify those square roots by factoring out all the perfect square factors. Okay, so square root of 18, I can rewrite 18 as 9 times 2. 9 being a perfect square. That's why I'm writing that. I could write it as 6 times 3, but neither of those are perfect squares, so that doesn't help me. But 9 times 2, and then this becomes the square root of 9 times the square root of 2. Square root of 9 is the square root of 3 squared, or 3. And this is 3 square root 2. So that's 3 times the square root of 2 there. Okay, 44 is 4 times 11. So this would be equal to the square root of 4 times 11, which is equal to the square root of 4 times the square root of 11, which is equal to 2 square root 11. Okay, square root of 169 is equal to the square root of 13 times 13, or 13 squared, which is just equal to 13. So for that one, we didn't really need to use our rule, but we just know that it's a perfect square. Square root of 75. Okay, so I can see a factor that's a perfect square in there, and it would be 25. And so I can write 75 as 25 times 3. So this is going to be square root of 25 times square root of 3. So this is equal to 5 times the square root of 3. 13. Okay, let's do a couple slightly more complicated examples. 128. Okay, so for example 3, if you find all the factors of 128, you'll see that 128 is equal to 2 to the 7th. And so that's not a perfect square, okay? So we know that there's not two numbers that multiply together to give us 128, but it is 2 to the 7th. So what we can do is we can take pairs. So that's 2 as a factor 7 times, rather. So I'm going to call this 2 squared times 2, squared times 2 squared times 2, okay? So that is, what I did was I paired up the factors of 2, because then those will all be perfect squares. And so that gave me 2, 4, 6, 7. So really what this is I've used rules of exponents that we know to rewrite 2 to the 7th as this product of factors. So this is more than 2. So up to now, we've just broken our number into 2 factors, because that's what our rule was. Where is it? Right here. This just says 2 factors. But actually, it could be as many as you want. It could be 3, 4, as many as you need it to be. Okay, so let's look back at our problem. Okay, so we've got this. So we can rewrite this this radical as the square root of 2 squared times the square root of 2 squared times the square root of 2 squared times the square root of 2. Okay, and of course I've done this because now square root of 2 squared is just 2. Okay, and then this I don't have an exact number for, so I'm going to leave it in its radical form. And so I'm going to rewrite this as 2 times 2 times 2, which is 8, times the square root of 2. Okay, so that is the simplified form of the square root of 128. All right, so I'm going to show you a different avenue to the same result. Because really a quicker way to do this would be to recognize that 128 is equal to 64 times 2. Okay, so this becomes just like what we did before. So this becomes the square root of 64, which I know is a perfect square, times the square root of 2. So this is 8 times the square root of 2. Okay, so your result is going to be the same, but it's all what you, how you think about breaking that number apart. You know, here we broke it apart as 2 to the 7th, and here we broke it apart as 64 times 2. They are the same number. Okay, we can do the same thing with this one. I think that a lot of you are going to recognize that this is 144 times 2. And that becomes the square root of 144 times the square root of 2, which is 12 times the square root of 2. Okay? But we can do this like we did this one. 288, if I get the prime factors of it, which is something that you know, would be a strategy that would be a good thing to do if you don't know how to break a number apart, is to find its prime factorization. And 288 is 2 to the 5th times 3 squared. Okay, so that 3 squared is a perfect square factor already. And the 2 to the 5th I can break apart and write as 2 squared times 2 squared. So that's 2 used as a factor 4 times. So I've got an extra 2. And then I've got the 3 squared. So you can see when we take the square root of this, so the square root of 288 is going to be the square root of 2 squared times the square root of 2 squared times the square root of 2 times the square root of 3 squared. Okay, so this is going to give us square root of 2 squared is 2. And again, 2. Here's our square root of 2. And the square root of 3 squared is 3. So you can find, you're going to see that if I take the 2 times the 2 times the 3, I'm going to get 12 times the square root of 2, which is the same result as over here. Okay, so I like both of these examples because they show that it doesn't matter what factors you find, as long as you're finding those square factors, you're going to be able to simplify the square root. The only problem would be is if you don't find all of them. And prime factorization is a good way to find all the square factors, is by writing the number as a product of its prime factors. And remember, to do that, one of the common strategies is to use a factor tree and get started that way. Okay, so if you're not sure about factor trees, you can give me a call or check it out on Khan Academy. I'm sure you could find a video on prime factorization there. Okay, so exercises 5 through 8 are just a little bit more practice with this, and remember, you can approach these different ways and still get the same result. So go ahead and work on those, and then come back and we'll quickly correct them together, and then you can move on to the problem set. Okay, so hopefully you have attempted these problems before looking at my solutions. And so the first one is square root of 108. All right, it's not a perfect square. So that's a good question to ask ourselves first. Is it already a perfect square? So what we want to do is find all the perfect square factors. And so I can see that 4 is going to be a factor of 108. And 4 is a perfect square. So I'm going to start there. And notice that it's 4 times 27 is 108 is 4 times 27, but 27 also breaks down too, right? So I'm going to write this as 4, and instead of times 27, 4 times 9 times 3. And the reason I did that is because I recognize that 27, although it's a cube, it's 3 cubed, it has a square as a factor. So 2 of those 3's I'm going to write here as 9. Okay, so square root of 108 is equal to the square root of 4 times 9 times 3. And I can break those apart, times the square root of 9 times the square root of 3. So this is going to be 2 times 3 times the square root of 3, and I can rewrite that as 6 times the square root of 3. And when I get done, I'd like to look at my results and look at what's under the radical and make sure that there are no perfect square factors left. Because sometimes you can do these part way and then you get to this point and you realize, oh wait, there's another perfect square factor, and then you can just keep going. You can just, do it again and factor it out, okay? So this one, 3 does not have any factors besides 3 and 1, so there's no perfect square factors to take out here. All right, so let's look at 250, okay? Well, first thing I noticed about 250 is that it has 25 as a factor. So it's 25 times 10. Right? Okay, so 25 is my perfect square factor, so that's going to simplify under the radical sign. And then 10, the factors of 10 are 5 and 2, and so that's not going to have any perfect square factors in it. So I'm going to write square root of 250 is equal to the square root of 25 times 10. And now I can break those apart, times the square root of 10. And I know that I can't simplify square root of 10 any further, so this just becomes 5 times the square root of 10. Okay, and then 200, work with 200 now. So I know that with 200, 25 is also a factor of 200. So 200 is equal to 25 times 4. No, it's not. It's equal to 100 is 25 times 4. It's 25 times 8, right? 8 25s is 200. So now I'm going to want to do something with that 8, right? Because it has a perfect square factor. So I can rewrite 8 as 4 times 2. Again, anytime something's a perfect cube, you know it's going to have a perfect square factor, because this is 2 times 2, and then this is the third 2 right there. All right, so use your number sense and your creativity here and get it factored to the point where you can simplify it, right? So square root of 200 is equal to the square root of, I'll write this as 25 times 4 times 2. Okay, which is equal to the square root of 25 times the square root of 4 times the square root of 2. And that's going to be equal to 5 times 2 times the square root of 2, which is 10 times the square root of 2. All right, so I'm just simplifying, combining factors, breaking them apart so that so that whatever's left under the radical has no perfect square factors. Then this is considered fully simplified. Okay, the last one, 504, I'm going to break apart again. And I think I'll do this on the next page. Okay, this one I'm going to do by, I'll demonstrate the factor tree with this one. Okay, so here I know that 2 is a factor of this number. So 2 times 252 is a factor, and this one's prime, so I'll circle it. So 252 divided by 2. Okay, and this is 126. 126, there's still another factor of 2 there. I like to take all the 2's out first, because then that just makes it simpler. So this becomes 63, 126 divided by 2. Now I don't have any more factors of 2, but I can see that 63 is divisible by 3, and that would be 3 times 21. 3 is prime, and so 21 factors to 3 times 7, which is prime. So 504, so the square root of 504, I'm going to write this as the square root of its prime factorization. So I have 2 to the 3rd power times 3 squared times 7. All right, so what I want to do is arrange these in all the perfect square factors. There's nothing I can do with 7. 3 squared is already a perfect square, so I'm just going to rewrite 2 to the 3rd power as 2 squared times 2. And I still have 3 squared times 7. Okay, so this becomes, now I can break these apart. Square root of 2 squared times the square root of 2 times the square root of 3 squared times the square root of 7. All right, so now I've got square root of 2 squared is 2. Square root of 2 stays alone. Square root of 3 squared is 3. And the square root of 7 is not simplifiable, so I'll rewrite that as square root of 7. So now I'm going to simplify this. So I'm going to take the 2 and the 3. 2 times 3 is 6. Put those together. And now I've got a situation that's going to need to be dealt with, because I've got square root of 2 times the square root of 7. And we don't want to have 2 radical signs here. So what I'm going to do here is sort of use this principle where I can break it apart and go the other direction. So the square root of 2 times the square root of 7 is equal to the square root of 14. So this would be 6 times the square root of 14. And that would be my simplified answer, because the square root of 14 does not have any perfect square factors, because here they are, 2 and 7. All right, so you want to simplify it that way. So that one was probably simplest to do with the prime factorization method, but if you found factors another way, but there's only one way to write a simplified square root. And so as you check your answers, if yours matches, then your process was just fine. All right, so you can read the lesson summary. It just pretty much states what we've been working on. And good luck with the problem set.